Thank you very much for the introduction, and I would also like to thank all the organizers for inviting me. So I'm going to talk about Auslander-Gorenstein algebras, and we are going to focus on their connection to the Auslander-Reiten bijection. So first, we are going to look at a recent result which shows that these two homological notions are very closely related, and afterwards we will see how they can be interpreted in lattice theoretic terms, and then afterwards in linear algebraic terms. And the second part will be based on a joint work with René Marczinzik and Hugh. So in my talk, A will always be a finite dimensional algebra over a field K, and modules will be finite dimensional right A modules. The main definition for this talk is due to Auslander. So if we take an algebra and we fix a minimal injective resolution of it, then we call this algebra Auslander-Gorenstein if it satisfies two conditions. So first, we would like this resolution to be finite. And second, we have a condition for each term appearing in this resolution. We would like the term in degree I to have a projective dimension at most I. Now, these algebras have many nice properties. They are Auslander-Gorenstein, and they have some very nice CCG categories. But today we will only care about the property that they come with a distinguished bijection between their indecomposable injective and indecomposable projective modules. And the interesting part is how this bijection is given. So we take an indecomposable injective module I, consider a minimal projective resolution of it, and send I to the last non-zero term in this resolution. And this is what we call the Auslander-Reiten bijection. So let me remark that already the well-definedness of this map psi is quite a non-trivial property, because for this, for example, we need that this last term is indecomposable, which doesn't usually happen. And this motivated the conjecture of Marczinzik. So for this, let's assume that we are working over an algebraically closed field. And then he conjectures that being Auslander-Gorenstein for an algebra is actually equivalent to this map psi, which we defined above, being well-defined and being bijective. So a priori, this is quite surprising because there is no obvious reason why this should be true. But the first main result tells us today that this actually holds for quite a large class of algebras. So it is true for every monomial algebra, that is for every path algebra where we are only allowed to quotient out monomial paths. So we set quotient out an ideal which is generated by a set of paths. And this is also true for incidence algebras of finite lattices, which we will show in an upcoming work with Iyama, Kleinau, and Marczinzik. So we can see some evidence for the conjecture of Marczinzik, and this is also a motivation for us to study this map psi more closely. Okay, so let me continue by stating a result of Iyama and Marczinzik, who investigated these homological notions for algebras, which are incidence algebras of finite lattices, and discovered that these two notions have very nice lattice theoretic interpretations. So first, being Auslander-Gorenstein for an algebra is equivalent for the underlying lattice being a distributive lattice. And in this case, this Auslander-Reiten bijection also coincides with the row motion map, which is a very, very searched map in algebraic combinatorics and can be seen as a permutation on the vertices of the lattice. Okay, so we have now homological notions, we have lattice theoretic interpretations, and in the remainder of this talk, I'll show how one could reinterpret these, how you could see these notions on the Coxeter matrix of an algebra. So for this, let me remind you that the Cartan matrix of an algebra A, which has n simple modules, is an n by n matrix, whose columns are the dimension vectors of the indecomposable projective modules. Now, if A has finite global dimension, then this matrix is going to be invertible, and thus it makes sense to introduce the Coxeter matrix of such an algebra as minus the transpose of omega times the inverse of this omega. And remember, the goal is to see these homological notions on this Coxeter matrix. And this is exactly what we do in our paper with Marczinzik and Thomas. So the nicest results we get, again, if we restrict ourselves to the class of algebras, which are incidence algebras of finite lattices. And I also have to tell you that to build a Coxeter matrix, we actually have to make a non-trivial choice. We have to order somehow the simples and then the indecomposable projectives of the algebra. And for representation theory, this often doesn't matter that much which ordering we choose. However, for these results, it will be very important to state the correct order. So let me say that in this case, we will fix an order on the vertices of the lattice, which is a linear extension of the order which comes from this lattice. And then we can build a Coxeter matrix with respect to this ordering, and we get the result that in this case, an algebra is Auslander-Gorenstein if and only if this Coxeter matrix can be written as a permutation matrix times an upper triangular matrix. Moreover, we also get that in this case, the map psi is going to coincide with the permutation which is associated to this permutation matrix P. So in conclusion, we can translate both of these homological notions into some factorization property of our Coxeter matrix. And let me also emphasize that actually this result is also quite easy to check. So if you have a Coxeter matrix, this just says that this is upper triangular up to reordering its rows. So this is a condition which is much easier to be checked than actually checking the original homological definition. Okay, so this last result with the Coxeter matrices gives us then the idea to generalize this notion psi. So the idea is that to take any algebra A with finite global dimension and associate a permutation to it, which would then generalize this map psi, or from a lattice theoretic point of view, we can think of it as generalizing the row motion map. So the idea is to go via the Coxeter matrix. However, not every Coxeter matrix has a PU decomposition. What we can do instead is we can take a Bruhat decomposition, which exists for every invertible matrix. Thus, which means that we can write it as an upper triangular matrix, a permutation matrix, and another upper triangular matrix. And what is true for the Bruhat decomposition, that this permutation matrix P is uniquely determined by the matrix C. Thus, it makes sense to associate to this matrix C the permutation P and call this the Coxeter permutation of the algebra A. Okay, so this is almost a complete definition. However, there is one important step missing. So the question is, which order of the simple modules should we choose so that we get a meaningful generalization of the map psi, meaningful so that it preserves some homological properties, or from a lattice theoretic point of view, so that it preserves some interesting properties of the row motion map. So for lattices, there was a canonical choice, and we were lucky that it worked very well, and we got what we wanted. However, for general finite dimensional algebras, there is no canonical ordering which we could choose. So a priori, this is a proposal of the definition, which is not complete, but I would like to state it as a last statement that there have been some recent results which show that for certain classes of algebras where there is a canonical choice for the ordering of the simple modules, and there is some notion for generalization of psi A or the row motion map, our definition seems to be the correct definition to generalize psi or the row motion map. So this is the case for linear Nakayama algebras or semi-distributive lattices. And this was everything I wanted to say. Thank you for the attention.